In this lab, I'll introduce some practical aspects of resistors, resistance, and Ohm's law. This will include experimentally generating a resistor's voltage current characteristics. The techniques we'll introduce here can be applied to automatically generate the IV characteristics for an arbitrary circuit element. This process is commonly called curve tracing. Resistors are usually used in electrical circuits to limit current or to set voltages to desired levels. Resistance is a property of materials which, as the name implies, measures how much the material resists the flow of current. Since voltage is used to cause current to flow, resistance indicates the amount of voltage required to move a given amount of current through a material. So less current flows through a high resistance than through a low resistance if the same voltage is applied to both. Resistance has units of ohms, which are represented by the Greek letter omega. Typical resistance values can range from ohms to thousands of ohms or millions of ohms. Thousands of ohms are called kiloohms and are represented by a K prefix, while millions of ohms are called megaohms and are represented by an M prefix. This is the symbol for a resistor. Resistors can have some voltage difference, V, across their terminals, and a current I entering the positive voltage terminal. Circuit elements are described by the relationship between voltage and current at their terminals. For resistors, this relationship is Ohm's law. Voltage is equal to current times resistance. In the lab assignments, we'll be mostly interested in the practical aspect of things. So in this video, we'll emphasize the measurement of resistance and some good data acquisition and analysis practices. There are several ways to determine the resistance of a given resistor. Resistors often have their nominal resistance encoded directly on them in some way. For example, many resistors have a series of colored bands painted on them which provide a code from which you can determine the resistor's resistance. The values printed on the resistor are, however, not entirely accurate. The actual resistance will almost always differ somewhat from the expected value. Therefore, when we're presented with a resistor, it's beneficial to verify its resistance with some measurement. Probably the easiest way to measure resistance is with a digital multimeter. DMMs invariably include a resistance measurement function called an ohmmeter, which displays the resistance of a resistor to which it's connected. It's also possible to apply power to a resistor, measure the resistor's voltage difference and the current through the resistor, and use the relationship between voltage and current to calculate the resistance via Ohm's law. In this video, we'll talk at least briefly about all of the above approaches. This is a large wire-wound power resistor. Resistors like this one, which are physically large enough, will often have the resistance value printed directly on the side. This is a 6.2 ohm resistor. Notice that on this resistor, the maximum power dissipation is also listed, 10 watts. This is another fixed resistor. It has a resistance of 1 megaohms. Notice that the physical size of the resistor doesn't correlate to the resistance value. The physical size is more closely related to the maximum power that the resistor can dissipate. The 1 megaohm resistor has a maximum power dissipation of less than half a watt. So far, the resistors I've shown have been fixed resistors. That is, their value is a set value which can't be adjusted. Resistors with variable resistance are also available. This device, for example, is called a potentiometer, or a pot for short. These components have a resistance which can be changed by adjusting a screw on the side of the resistor. Most of the resistors we'll use in this course are these small carbon resistors. The resistance of these resistors can be determined from the colored bands on their side. Next, I'll talk about determining a resistance from the resistor's color bands. Resistors can have either 3, 4, or 5 color bands. This is a typical 4-band resistor. This means that the resistance value and its tolerance are coded in 4 colored bands on the resistor. The first 3 bands consist of a resistance value in exponential notation. The 4th band is the tolerance, which tells us the allowable error between the actual and nominal resistance of the resistor. The colors of the first 3 bands indicate the digits 0 through 9. Black is 0, brown is 1, red is 2, and so on. A complete table of colors is provided in the next slide. The first three bands are read as follows to get the nominal resistance. The general formula is shown here. The first two bands, A and B, represent a two-digit number which provides the mantissa of the resistance. The third band provides an exponent, or power of 10, by which the mantissa is multiplied. For example, if the first three bands are brown, black, red, the value is 1 for brown times 10 plus 0 for black, times 10 to the second power, since red corresponds to 2. This is 10 times 10 squared, or 1,000 ohms. The fourth band is the tolerance. It's a number that provides the maximum error between the expected and nominal resistance of the resistor as a percent of the nominal resistance. A gold band, for example, means that the actual resistance value will be within 5% of the value coded on the resistor itself. As I mentioned previously, resistors can have various numbers of bands. This table provides coding for all possible variations. I won't spend time on this, since if you can read a 4-band resistor, you can use the table to read any of the other codes. For a 4-band resistor, the first and second columns of this table indicate the mantissa, and the fourth column gives the exponent. Now let's take a look at an example of using the color codes to determine a resistor's nominal resistance, and then using a digital multimeter to measure the resistance. This resistor's color codes are brown, black, red, and gold. Brown is 1 and black is 0, so that's 10. Red is 2, so that becomes 10 times 10 squared, which is 1,000 ohms, or 1 kiloohm. Let's check the resistance with a DMM. In order to measure resistance, set the selector knob to the ohm symbol and insert the DMM leads into the COM and volt ohm ports. If the resistance between the leads is too high for our DMM to measure, as in the case where there's nothing between the leads, the DMM display reads OL. This stands for overload and simply means that the resistance is higher than the DMM can register. When I clip the DMM leads to my resistor, I get a measured resistance of 0.99 kiloohms, which is 990 ohms. Since the tolerance band of this resistor is gold, the measured resistance is well within 5% of the nominal value. Now let's use a DMM to set the resistance for a potentiometer. The maximum resistance for this device is encoded on the side of the pot as 3 numbers. The first 2 numbers create a 2-digit number. This 2-digit number is multiplied by 10 raised to some power indicated by the third number. Our potentiometer is encoded as 103, so its maximum resistance is 10 times 10 to the third, or 10 kiloohms. The actual resistance of the potentiometer can be adjusted to any value between about 0 and that maximum resistance by turning the set screw on the end of the pot. The potentiometer has 3 terminals with which to connect it to your circuits. The resistance between the 2 outer pins is simply the maximum resistance of the pot. The resistance between these pins does not change as you turn the set screw. The resistance between the center pin and either of the 2 other pins does change as you turn the set screw. Since this is a variable resistor, we can't tell what the actual resistance is without measuring it. Typically, we measure resistance with a digital multimeter, or DMM. Let's do that now and see how the resistance changes. To measure resistance, we set the DMM knob to the ohm symbol, plug the leads into the volt, ohm, and COM terminals, and then connect the leads to the resistor pins. I'll use the center pin and this outer pin. Currently, this resistance is about 5.2 kiloohms. If I change this screw position, the value of the resistance changes. Now let's talk about estimating resistance from a measured voltage and current. Ohm's law tells us that voltage is equal to resistance times current. If we rearrange this, resistance is the ratio of voltage across the resistor to the current through the resistor, or R is equal to V over I. This is a circuit we can use to measure resistance. It consists of a voltage source used to apply power to the circuit and an ammeter to measure the resistor current I. If we measure the voltage V across the resistor, we can use that measured voltage and the measured current to estimate the resistance by taking the ratio of the voltage to the current. I'll demonstrate this process next. This is the really simple circuit I'm going to use to estimate resistance. I've simply applied 5 volts across this resistor. First, I'll measure the voltage across the resistor by plugging the DMM leads into the volt-ohm ports and the COM ports. The function selector is set to V with a bar over it. Now I can just connect the leads across the resistor, the positive lead at this end and the negative lead at this terminal. Turning on power gives me a voltage of about 5.1 volts. That's about 5 volts as we'd expect. However, don't trust the voltage source to deliver exactly the voltage you're expecting. Real sources are not ideal and can deliver a voltage that's significantly different than you expect. Make sure you measure the voltage itself. Now I'm going to turn power off and change the circuit to measure current. To measure current, I connect one of the leads of the DMM to the A port and the other to the COM port. I set the function selection knob to A. To connect the DMM to the circuit, I need to break the circuit apart so that the current is sent through the DMM. To do this, I'll disconnect this jumper here, connect the COM terminal to that jumper, and the A terminal to this terminal of the resistor. Now the current will come through here, through the resistor, into the A port of the DMM, out of the COM port, and back to ground. Let's turn on power and see what we get. I get about 0.015 amps or 15 milliamps. I can now estimate the resistance of this resistor by dividing the measured voltage by this measured current.